Alright, hello and welcome to a new week. So this time we're going to be talking about containers, the magical world of containers where you can hold a bunch of different things. Alright, the first thing that I want to talk about though, before we get there, psych, is the final. So let's talk about the final and the extra credit because we're getting close to the end of this semester. You're almost done. Alright, so what I'd like to do is talk about this module. So week 18, there are no classes. It's just the final. All right, so I've made this module and I'll make it available to you. And so there's going to be a final info page and an extra credit assignment page. So let's go to the final info page first. So here's the idea. The final will be made available on finals week, the Tuesday. Okay, May 18th is a Tuesday, so plan for that. And it will be available at 2:30 just like the midterms have been, okay? It's just a Tuesday this time. This is May 18th. It is the Tuesday, and the Wednesday is the 19th, so you have over 24 hours to get started on it, okay? So it's due at the very latest 5:30 on the 19th, and you can start whenever you want. As usual, you get 2 hours this time. Finals. They're scheduled to be, they're supposed to be, if we had a real classroom, an hour and 50 minutes. So I'll write the final with that in mind, and I'll just give you 10 extra minutes for fun. So use them if you need them. That is the idea there. And so the topics are all this stuff. It's going to be cumulative. This final is, it's a heavily weighted assignment, and so it's going to be taken from everything, all the questions. And so all the Zybook readings, all the Zylabs, all the virtual machine labs, all that stuff. But I will try not to be a horrible person, and I'll give slightly more weight to the topics that we've covered after the second midterm, because those are the ones fresh in your mind, right? But you should still expect to see a little bit of everything, because this class, everything builds on top of itself, right? You should definitely expect to see functions in classes for the rest of your life, right? That's the idea. So yeah, here are all the topics you should be familiar with. Prepare, yell at me if you have any questions. Of course, I'll give a review. And then all the stuff after bitwise operations, like the stuff I'll talk about today, that is not as important in my mind to hit hard on the final, because you'll learn about this stuff in a future class if you take a future class. So you should still expect to see questions on the stuff that I'm going to be covering from now on, but I'm not going to focus on them too much on the final, and if I do, they'll be easy questions. Okay, that's the idea. That's my promise to you. And so yeah, the format is going to be exactly the same as usual. Multiple choice questions and fill in the blank stuff. I do get your multiple choice questions from the book, so I kind of like fiddle around with stuff that's in the book, so expect to see a bit fewer of multiple choice questions because there aren't a lot of chapters left to test you on. It's just these, right? So yeah, everything is the same as before. Open book, open notes, go crazy, but don't talk to another human. Okay, that's the idea. So yeah, that's the final. And oops, I noticed that I forgot to talk about the extra credit. Excuse me, here I am talking about it now. It's essentially the same as the last two extra credits. It's going to be worth up to 5% this time though, so it's the last one. Let's finish strong. So if you want to do the full amount, you get up to 5% extra credit. And so you have the same options: make a review video that goes over the concepts that will be on the final, or make a write-up with like all the questions and answers, giving some nice explanations of all the stuff. Yeah, so do either one, and if you want that 5% extra credit this time, you got to do double the 2.5%. So a 40-minute video or 1,000 words including code. Okay? So that is your extra credit, and now I will horribly transition back to me in the past. So I will see you then. And now let's get into the meat of today. We're going to talk about containers, storing stuff. That's what a container is in C++. It's all a metaphor as usual. And here's a funny meme before we get started. All right, onward we go. So the first thing that I want to talk about is this concept called an abstract data type, okay? And that will lead into, naturally, this idea of containers, all right? So an abstract data type is shortened to ADT a lot, so you'll see that. And it's just a class, not like a C++ class, just like a logical conglomeration of things. It's a type of object whose behavior is defined by a set of values and a set of operations, okay? That is the idea. That is what an abstract data type is. It's like a black box. So let me explain it that way. So here's our black box, and let's pretend that this is a class that I give to you in C++, like a real class this time. I define it as a class. And that's essentially what any library is, right? You make a class, it's like a black box, and you can ask it to do things for you. Like, hey, if this is like the vector black box, it's like, hey, push back 2, please. And it will respond back with you to you saying, okay, sure, I got you. And then you can just play this game as much as you want, contacting and messaging this black box. It's like, okay, what is your @0 now? And then it's going to say, oh, it's 2, because I was empty before, okay? As long as you make a black box that responds in this way to these kinds of operations, you have a vector, right? I didn't mean to get philosophical, but I guess we have to in this lecture. That's all a vector is. It's just it's a black box that responds to vector questions. Yeah? That's the idea. So we don't care. We actually don't know. I've never really talked about it. We don't know or care about how this thing is implemented. So vectors, for example, they are just a black box to us so far. If you take CSCI 41, they will be less of a black box. We'll implement them there. Vectors are just these boxes that respond to these messages. Pushback, popback, size, all this stuff. You can write your own vector as long as it responds to these things in the right way, in the way that a vector would, you know? That is it. This is the vector black box. And that is the idea of an abstract data type. It's something that you don't know how it's implemented, but you just know how to respond, or how to message it and how it's going to respond back, okay? Which is like a .h file. That is what abstract data types are, okay? And a container, now we're ready for it, is just a type that holds elements, okay? So it's a box that is not as black because we know that we're putting stuff inside of it, right? We can put the 2, we can put the 3, we can put the 4, and maybe there's some type of order, but how it keeps track of that order, we have no clue, okay? We don't know about the implementation still. It's just a container, it holds things. So a vector, it's a container. It's holding the 2 that we put in, it's holding a 3 that we put in, and it keeps track of orders and sizes and things like that, okay? So yeah, vectors are containers. You can even put a vector inside a vector, multiple vectors inside of vectors. How does it do it? We won't know until CSCI 41. Yeah, that's what a container is. And so we'll talk about a bunch of different kinds of container classes implemented in C++, and like how we can talk to them and what they respond back with. Okay, and that's the idea. And we'll study this topic a whole lot in CSCI 41 if you choose to take that. Okay, that is the idea of abstract data types and containers. Now, let's get into vectors, okay? Because that's like the quintessential example of like what's going on here. Okay, so a vector, it is called a random access container, which means you can access any index you want. You can go straight to index like 0, 1, 2, 3, 4. You can go straight to index 2 if you want and like get the value that's there. That's the idea. Okay, that's what random access means. You can go to anywhere, any index you want, and yeah, that's what you get. You get an index and the ability to index into a vector. But still, we look at it like this. We think about it as an array, but really we don't know. It could be anything as long as it responds to those vector questions in the right way. So let's look at vectors. This is the documentation for them. Maybe I can make it bigger. So yeah, they look all like this, and if you read into this, it talks about a little bit how it's implemented, okay? But really, all we need to know is that it's a class and then it responds to these kinds of questions, okay? That's the idea. So we talked about how to figure out the running time of things, and we talked about like linear operations and things like that. There is a kind of operation that is very fast. It's called constant time, and it's the best possible complexity for an operation. And it just so happens that a lot of vector operations are constant time, like @. Going to an index and getting the value there for vectors is constant time. If I click on this, it says somewhere it's complexity, constant. Now you know what this section means. Just read this as super duper fast. We like constant time things, okay? Size is constant. Pushback is actually constant. It's a weird kind of constant that I can explain later if you're interested. But it's still constant. These are all fast things to put values into a vector. If you push something back, it's going there really quickly. That's the idea. Okay? And you can use .at, you can use .size to use a for loop to get around a vector. That is what a vector gives you. Okay? We've used it like this so far. But vectors, I've showed you how to sort a vector, and it needs weird functions to be called, weird methods to be called begin and end, right? And these are called iterators. And now it's time to learn what these really are. Okay? What is an iterator? How do we use them? Okay? That is the idea. So iterators, an iterator for a vector, it's just, well, it's an abstraction over the concept of iteration, which is kind of a circular definition, isn't it? They're modeled after pointers, though, which is nice. So let me show you how to go through a vector using iterators. Okay? The idea is, if you have a vector, here it is, I want you to think of these things called iterators that I'm about to show you as pointers. Okay? Think of them as pointers, because we're going to make a vector iterator. It looks like this. That's the type, called it or something. And what it's going to do is it's essentially a pointer to where you're looking in the vector. This is the begin. Okay? Right now this is the begin part of the vector v. So this would be iterator right now equals v.begin. That's the idea. That's where it's currently pointing. And then we have the concept of the end of the vector, v.end. And that, it doesn't point to the last element, it points to one past the end, which is weird to think about. That's okay. And they are kind of like pointers because if you say star it, wherever your iterator is pointing, it will go there and get back the value. Okay? So it'll give back 1 in this case right now. Okay? So that's a lot of talk. Gave you a little bit of an introduction to all this stuff. Let's fully understand what all this means now. Okay, let me give you an example for real. So if you click on the begin part of the vector, it shows you a nice little example of using iterators and all this cool stuff. But I'm going to show it to you now. Are you ready? So think of iterators like pointers. Pointers to elements inside your vector, inside your whatever container you're using. Okay? So vim vectors, vector iterators dot cpp. So let's do this. Definitely going to need vectors, and let's make a vector. Okay, vector int v equals, I don't know, 1, 2, 3. A simple little vector. And now I'm going to iterate through the vector. Using not pointers, but iterators, which are very similar to pointers. Okay, so what we do is, I'll use a while loop this time. You can use for loops too. Maybe I'll do that later. What you say is you first get a iterator to the beginning. It's like a pointer to the first element. So vector, and the type of an iterator, it depends on the type of the vector. So if it's a vector of ints, it's vector int : iterator. Okay, and then I usually call it it, and it starts at v.begin. Okay, it starts at the beginning, and then we're going to iterate while it is unequal to v.end, because that would mean it's 1 past the end. It's not the end, it's 1 past the end. So while it is unequal to v.end, because all these vector operations, these iterator operations, they return back in iterator. Begin and end both return back in iterator, and we can compare those. While it's not equal to v.end, we're going to cout star it, so getting the value at the iterator, they overloaded the star operator. Is like dereferencing. And then we want to advance the iterator, advance it, to go to the next element, to look at the next element, and that's how we'll iterate through everything. So we just say it plus plus or plus plus it. Either way works. Okay, and so it really is very similar to pointers and pointer arithmetic, but that is the idea. And then you can say it plus plus, and that moves it to go from there to here now. And now if you say star it, you're going to get the 2 back. Okay? So it's all very similar to pointers. We start at the beginning, point to the beginning, while we're not equal to 1 past the end, like dereference our iterator, and then advance it to then point to the next element in the vector. Okay? That's the idea. And I think you can imagine what this is going to print out. It's going to go through in order, 1, 2, 3. Okay, that's another way of traversing this vector, going through it. It's using iterators. And you know that range-based for loop with the colon and everything? It's really secretly being translated into a use of iterators. Okay, so that is what iterators are. And so let me give you one big example for like what was going on in our program. Okay, so our vector was 1, 2, 3. And then we started our iterator, it, at v.begin, which is essentially pointing to the first element. And then we said, okay, star it, which prints out on our screen the element that it, the iterator, is looking at. Okay, so just think of it as dereferencing. And then, might as well use a different color, we say it plus plus, and that told it to look at the next element. Okay, so it is now pointing to the 2, and if you said star it here, which we do in the while loop, it will now print the 2, it plus plus. We see the 3 now. That's where it is looking, and then star it will print the 3. We'll get the 3, and then we can print it with cout, that is. And then we finally say it plus plus one more time, and that pushes it to point to or look at 1 past the end of the vector v. And that is somewhere we don't want to look at. We want to stop and not dereference here, okay? Because that's kind of like a segfault. We don't want to do that. And let me give you an example of what would happen if we did star it. It may or may not work, but it's either way, it's undefined behavior. This is a bad idea because it's 1 past the end now. Whee! So it looks like we got lucky and it was a 0, but oh man, oh man, oh man, this is undefined behavior. We don't want to do this, okay? Don't ever do this. Even though it doesn't crash your program sometimes, it will burn you. All right, so that is vectors and their iterators. Now let's talk about some other C++ containers. All right, we have some other ones, and the next one is called list. Okay, so let me go to it in the documentation as well. There is a container, there's a header called list, and it has a type involved in it called list. Okay, this is the class list defined in the list header, and it's very similar to, like, it works in almost the same way as like a vector. You can get the size, you can push back and things like that, but lists are a bit different, okay? And they're a really, really good example of why iterators are useful, okay? Because life doesn't always hand you a vector where you can just use .at, okay? So the question that you might ask is, like, why would I ever want to use these iterators? They look complicated, they're weird, and the reason why, the main reason why you'd ever want to use these, the reason why it's a very good idea, is that they work in the same way. They abstract over going through a data structure, and so they work in the exact same way for vastly different containers. So a list is a different kind of abstract data type. It responds to similar commands to a vector, but not the same ones. There's no concept of indices. There's no .at, but there is like push back, pop back, push front, pop front, and size. Okay? And the times are a bit different. If you want to insert or delete to the front or back of a, I think I should put front in that one. I think the front's the more surprising thing. So maybe I should say back or front. Because it's really hard to delete from a vector the first element. Because you got to shuffle everybody over, you know? They all got to move that way. Lists make it constant time to do all of that. And you've actually learned about the list data structure, the linked list data structure, that is. So all this stuff, push front, pop front, they're all constant time. Look at that. Constant time. Crazy. Constant time. Crazy. And I do encourage you to read about this kinds of stuff for lists. Constant time, insert and erase operations anywhere in the sequence. You can iterate in both directions. It's wonderful. It's a bit different to vectors because, let me show you vectors again. Do vectors have a pop front? Vectors don't, first of all, don't even have a pop front. So that's a good enough example of why lists are necessary. You can use erase to get rid of something, but the complexity is linear. See, that's worse than constant. That's for vectors. Okay, so this is what a list looks like. It's like a linked list. So if you want to push 1, 2, and 3, the nodes look like this. 1, 2, and 3. And this is why it's really easy to add something at the front. You just make a brand new node, all shiny and new. And you can just like hook it up to the next element because it's secretly using pointers deep down. So that's the list, abstract data type, and it responds to these kinds of questions. And so let's have some examples of a list. So edit lists.cpp. Let me make a list for you that also holds 1, 2, 3. Okay, so instead of including vectors, I'll include list, and we'll say list. I'm going to make a list with ints inside, L, and it's going to start out empty so that I can show you all these different cool functions. Okay, so we can totally like push back things as normal. We can push back 2, but about 3. So now the list just contains 3, just with 3 in it. Now we can push to the front. We can push front 2. So now the list is got a 2 in front of the 3. Yeah? We can push front 1. Now the list got a 1, 2, 3. We can push front 0. Now the list looks like 0, 1, 2, 3. And we can pop front as well, and then I'll delete the thing at the front. And so now the list is back to just 1, 2, 3. Okay? Isn't that cool? That is what lists can offer to you. There's no .at, but with lists, usually you're only caring about like the last element or the first element. And if you want to iterate through, it doesn't really matter because we can use iterators. Are you ready? So yeah, these are lists, and we can go through them with iterators. Okay? Even though there's no .at, all of these iterators work in the same way. Okay? That's the beauty of them. Okay. So here is my list again. We have 1, 2, 3. This is how I'll draw it. It secretly looks like this is a different kind of data structure deep down, but we can just think about it as a list like this. And the iterators, they work exactly the same. We can say iterator it equals list l.begin, and that'll have it look at the 1 if we said star it. Right? Set star it, it would give us back the 1, and we can print that out. And we can also say it++ to advance it to the next list element, which just brings it over here, however the data structure is arranged. Like this doesn't look anything like a vector anymore, and yet it knows how to get to this next thing. That's the beauty of iterators. And then if we said star it here, it'd print the 2, increment IT, sorry, IT would get the 3, increment IT, it would go 1 past the end, which is nowhere, and then we know to stop. Okay? That is the beauty of it. Okay, so yeah, this is the idea. So yeah, let me show you the for loop way of iterating through this using iterators. For, you have list int : iterator. This is the full type of iterators. It depends on the type of the list of ints. Okay, so list int : iterator. That's the full type. Call it it. Start it at l.begin while it's unequal to l.end. Do the body, and after you're done with the body, do it++. Yeah, that is the goal. That is the beauty of it all. And so we can say cout star it, and we'll get our 1, 2, 3 out of the deal. So let's do list -o lists. Oh yeah, isn't that nice? So that is lists in a nutshell. Let us move on to using the range-based for loop this time. Okay, let's try the range-based for loop, because this is exactly what's happening under the hood when you do this. Okay, this is what the range-based for loop gets translated into. So you remember this, you can do it with vectors and lists, anything that can be iterated through. You say int I or x or whatever, go through every integer in L, call it x, cout x. So these are all the same. Let's do that. So the following right here, it gets translated exactly into this. Okay, that's what's happening under the hood. And so that's why the range-based for loop works. It's just it's called syntactic sugar for something more complicated. So it's nice and sweet that we can use this in contrast to this. But you know what's really happening now, which is nice. So it does the same thing. You can also go backwards. You can start at the end. So if we want to go backwards, we can just essentially use most of this, and we can use it minus minus instead. Isn't that crazy? So I think a while loop is going to be a lot better here. We could say, because we have to do weird things. So, but it is possible. Start at the end. Oops. And we don't want to start at the end. We want to start at the last element. This is 1 past the end. So we have to do it minus minus so that we're actually at the end. And then we can say, I don't know, probably while true is the best thing to do here. Yeah, that would work. Then we can say cout star it, and then we can say it minus minus, I think, and if we're ever at the beginning, if we just printed out the beginning element, we should stop. If it is equal to, we just print out the l.begin, maybe we should break out of this loop. Otherwise, continue after decrementing your pointer. So this is how you can use iterators to go backwards. You're not really supposed to use them like this. 3, 2, 1, it works. Cool. But that's okay, we can break the rules. It's a lot easier to use what's known as a reverse iterator to do this, because then you can just use r-begin and r-end instead of all this weird stuff. Look into the reverse iterators, r-begin and r-end, because r-begin is like the last element. R-end is like 1 past the first element. It all works in the way you'd think. Okay, so that is iterators, potentially reverse iterators, and lists. Okay, isn't that nice? So those are lists for you. And yeah, now it's time to talk about this wonderful, wonderful type called sets. Okay, are you ready? Now sets, they are fun because what they store, they're like a cloud that it stores their elements. It doesn't matter if you like add in 2, then 1, then 3, then 0. It's going to store them eventually as, well, first goes the 2, then it knows to put the 1 there, then the 3 here, kind of, and then the 0 here. It stores them all in order. It's crazy. So when you iterate through it, it'll give you back the numbers in order. Isn't that fun? So that's what a set would give you. Yeah, sets are different. They're very different to lists and vectors. Lists are very similar to vectors, but sets are like something new and cool. They have different things. It's a different kind of data type. It responds to different questions. It's in the set header called set. And it has still size, of course, but there's no like push back. There's no pop back because there is no front and back. It's going to put it in order. So there's insert. That's all you need. Isn't that nice? So there's insert. There's see if it's in the set by counting. See if it's there. Things like that. It's a very, very nice thing. All right. So maybe if I show you the constructor, it might have a nice example here. So yeah, look into all this stuff. Sets are wonderful. Insert is usually how we add things to sets normally. Okay, so maybe we can insert like that. That's the idea. Okay, so let me show you this. Let me show you all this stuff. When we do insert, when we do see if something is there, when we do erase things, these operations, they're not linear time. They don't have to look through all the stuff to delete the 2. They don't have to like figure out by looking through everybody where to put the next value, like maybe 1.5 needs to go there. They kind of do a binary search in a sense, okay? And if you take CSCI 41, again, hint, hint, I will tell you all about this cool thing called sets. We'll kind of implement their back-end data structure. So all these operations, they're logarithmic time. So they're in between constant and linear. Okay, they take what's called logarithmic time. So where is complexity? Logarithmic in size in general. So if I want to add another, add the 1.5 to this set, it's going to take log base 2 of some constant times log base 2 of 4, because that's how many things were in it before, time. Okay, this many instructions, this many basic operations. Okay, so that's what sets are, and yeah, they know the order of their elements. It's wonderful. Okay, so let's try insert and count and erase. Okay, edit sets.cpp. So we're going to include set. So we can make a set of, let's do doubles this time, because why not? Set of doubles, call it S, and it starts out empty, and we can add stuff. S.insert 42.5. S.insert, I don't know, 3.14. How about that? And now that these are in there, we can ask, hey, are you there? Count how many 42.5s there are. Count how many 2.71s there are. So it should be 1 and 0. Isn't that nice? Let's count. You can add whatever you want, insert whatever you want. And you can remove whatever you want. So you can say, okay, let's get rid of the 42.5. You can say s.erase. Give it the 42.5, and then it will no longer be there. The count is gone. It should say 0 now. 100. Okay, so that's sets in a nutshell, and it's secretly, when you're asking it all this stuff, kind of sorting it and then using it like a binary search to see if it's there and to get rid of it. So because that, we can, when we iterate, when we use iterators or this range-based for loop, we're going to get back the values in order. Isn't that crazy? It's very useful if you ever want that. You don't know the order that you're being given things, but in the end, you know you want it sorted. A set is very nice for that. Okay, so let's do the long way first for set. It's a set of doubles this time, so this is what the iterators type is. Set double iterator, it, equals s.begin. It is unequal to s.end. And now you see the power of iterators. Like, this is just a cloud. I'm not even telling you how this is implemented, but it knows how to go through it. That's what iterators give you. It++, cout star it, new line. Let's give ourselves some space. Yeah. Okay. So it's got 1, 2, 3, and 3.14 in order. Isn't that nice? So that's sets, and then of course the range-based for loop works just fine. You can say almost the same. How about this? For every, I don't know, double D in S, print out D. Same thing, and it uses iterators and it goes through it in order. Okay, secretly this is being translated into this. So that's sets, and let's talk about maps, and that'll be the end of this little section. Okay, so a map is almost exactly like a set in that things are ordered, kind of, but it holds not just a single value, it holds pairs of values. Okay, so there's two types in a map. There's always a key type and a value type, and a map, we say that it maps keys to values. Isn't that cute? So for example, the most logical type of map that you'd like to have is like a phone book. So maybe you want to map the name of somebody to their number, right? And maybe my cat has a number as well. This will be, I don't know, 555 1235 this time. And so you can store these kinds of pairs of things with this being the key, the thing that you're going to use to look up in the phone book, and then this is the value. And it really is sorted, like everybody's name in the phone book is sorted. Isn't that nice? So, yeah, they're just as fast as sets because they're still like sorting things deep down. Yeah, so let's make a map with string keys, names, and int numbers. That'll be our phone book. Okay, and maps look like this. We have containers, maps, bam, and to add things to maps, we, instead of using insert which exists, we prefer to use in place. Okay, that's a nice, cool new thing that makes it easier to insert keys and values into maps. Okay, so yeah, all very similar stuff to sets. Maps.cvp. So you can make a map, call it phone book, and I'm going to need both maps and strings because I'm having string keys. Okay, so if I want to insert stuff into the phone book, I say phone book.inplace and then a name and a number, the key, and then the number. Yeah, that's the idea. And of course I spelled my own name wrong. So now we have two elements in the phone book, and you can look them up. You're like, okay, let's see if I'm in the phone book. If phonebook.count of Lawton is there, if it's greater than 0, then let's go and get it out. Cout, let's get Lawton's number by saying phonebook.at Lawton. Okay? It's always good to check and make sure that the value is in the phone book. Okay, and so .at just gets you the value back that's stored that's associated with this key. Okay, so this is the key, this is the value, and so it's going to give me back, it's going to print out my phone number. Yeah? Isn't that cute? So that is maps, and you can, if you wanted to, you can totally iterate through them. Okay? So let me show you that if you're interested. But yeah, usually it's all about looking up these things. Okay? They are just as fast as sets. They are logarithmic time for a lot of things. It's in between constant and linear. It's quite fast. So yeah, that is the idea. It's logarithmic, we can iterate through. It has iterators, and I believe it's going to go through the keys in order. Okay, so we can go through it just like this, and the iterator this time, it has two things to give you, so it's a bit different. So for I don't know, we need to make the iterator first. Map string int iterator, because it's always the type : iterator. It equals phonebook dot begin. It's unequal to phonebook dot end, and then it plus plus. So now, when we have something in it, it doesn't have just the value, it has a key and a value. So it holds them in it arrow first, because it is like a pointer, right? It arrow first and it arrow second. Okay, so the key is in the first one, the value is in the second one. Cout it arrow first, and then maybe it'd be like colon space it arrow second, and L. Yeah, and so this will print out the name and the number after a colon. Isn't that nice? And so it's in order, alphabetical order for strings, dictionary order. And that is the idea. That is the idea of maps. And of course you can use the range-based for loop for this as well. Again, though, you're going to get back a pair of things. Okay? It's going to be a pair, which is a type that you'll have to look into if you want to do it that way. Okay, so that is maps. And I think that's all I wanted to say about them. They're always about holding those two things, these keys and values, okay? Key and value, which is quite nice. Nice to have all this stuff. Okay, so that is maps and their iterators. I think this is where I want to stop for now, so we'll come back and finish up these slides really quick in the next lecture, and I will see you then.